Gas vapor mixture and air conditioning. So gas, when we say gas, it means there is no chance of condensation. It's gas. So here we are talking about air and vapor. Inside the air, there is water which may condense. Okay, so that's why it is called gas vapor mixture, right? The chemical nature of both will remain same. There is no chemical reaction going on. That's why that is called gas vapor mixture. And how this is important for air conditioning processes or air conditioning calculations. Okay, because in air conditioning we are treating air, normal ambient air, and this ambient air is not just dry air. There are water vapor in it, and that water vapor plays a very key role in determining the comfort condition of for us human beings. Very humid or very less humid, that will affect our comfort. So that's why it is an important part which we cannot neglect when we are dealing with air for air conditioning. Okay, so you have to be sure how much water vapor is there, how much water vapor you want to add or subtract to have a comfortable condition or space. Okay, so in this chapter we shall just cover the basic definitions which are used in the calculations of these gas vapor mixtures in air conditioning. Okay.
You will not study the cycle of air conditioning. It's only how the
basic definitions. So we start with this concept which we already know, dry and atmospheric air. So here TV or TS, so below this temperature, gas phase of a substance is frequently referred to as vapor. Above this, it's all gas. But below this, there is a chance of condensation. Okay. So at temperatures below critical temperature of a particular substance, gas phase, we use the term vapor below critical temperatures. Term vapor also implies that if it may condense, okay, at any point during any process, if you are near the dome, okay, so then we use the term vapor. We already discussed this thing. So now we are dealing with gas vapor mixture. It means there is a gas, there is no chance of condensation, but there is another gas which may condense. Okay, so what we are talking about, atmospheric air. So our atmospheric air is not pure dry air. There is water vapor in it. So air in the atmosphere contains some water vapor or moisture in it. So whenever we say dry air, the term dry air means no water vapor at all. Okay. So that's why we have to treat this air as a mixture of water vapor and dry air, because the amount of that water vapor in this dry air is not constant. It keeps on changing depending upon the weather conditions. So this water vapor plays a very important role in the air conditioning applications, because we have to know exactly how much vapor should be in that air in which we feel comfortable. Okay. So dry air is clear and atmospheric air is clear. Atmospheric air means dry plus water vapor in it. And when we use the term only dry air, it means without any water vapor. So atmospheric air means both dry air plus water vapor. Dry means no water vapor. Okay, in air conditioning applications, the maximum temperature limits in which our air conditioning systems are working is normally in this range. For any air conditioning application, what we are doing, we are heating the air or cooling the air. So if you are heating the air, maximum you could heat it up to never 50, but the upper limit is 50. And when you are cooling the air for air conditioning purpose, not for refrigeration, air conditioning purpose, it will be up to 0, but we are taking up to -10. Maybe in some cold storages, we use very cold air for food storage, okay, for air conditioning. So that is normally the limit of air conditioning applications, not for refrigeration. Refrigeration applications, you can have -250. There are refrigeration systems which can produce -250 up to it. So that is refrigeration. For air conditioning systems, that is the range normally. All air conditioning processes, they are operating under this range. Now in this range, the air properties which we need in the calculation of air conditioning, the CP value can be assumed constant. There is no worry of using variable specific heat of air. This changes in the third decimal, and that is negligible. Okay, that's what we are trying to say. Okay, so you can calculate enthalpy of dry air using that equation at any temperature for the change in temperature Cp into delta. So you are using that averaged Cp, this averaged Cp multiplied by whatever is the temperature change to calculate the enthalpy change. Okay. Okay. Water vapor in that air is at very low pressure. We discussed in the last chapter of combustion that water vapor is at very low pressure, and it also behaves like an ideal gas because it is at very low pressure. Atmospheric pressure is 100 kilopascal, but in this 100 kilopascal, the partial pressure of water vapor is very low. So that's why water vapor behaves as an ideal gas in that air. Okay. So now here we can define two pressures in that atmospheric air. One is the partial pressure of dry air with no water vapor, and the second is partial pressure of water vapor. So the total pressure of atmospheric air consists of two parts, dry air and water vapor. Partial pressure of water vapor is also named as vapor pressure. Okay. So at 50 degrees Celsius, so what is the maximum temperature which we have to deal with in air conditioning? That is 50 degrees Celsius. So 50 degrees Celsius, what is the vapor pressure? So this is, for example, 50 degrees Celsius. So water vapor in that air will be somewhere here at 50 degrees Celsius. What is the maximum possible water vapor pressure in that air? This one, or lower than this. If water is vapor in that air at 50 degrees Celsius, so it will be here or less than these pressures. Okay. So what is that pressure? That is 12.3 kilopascal. So it means your water vapor in that air will be at this pressure maximum or lower than these. For lower pressures, for lower temperatures, the pressure is even lower than this one. So maximum pressure of water vapor in that air, if air temperature is 50, maximum is this one. So if you go, it could be low, but maximum, we are talking about maximum. So if you go to that chart of ideal and non-ideal gas region from chapter 3 of Thermo 1, so you will see below this pressure, this water vapor is ideal in this whole region. Why we are saying that this water vapor in that air, atmospheric air, is ideal? Why? Because this is the maximum pressure of water vapor. If it is vapor, higher than this, it will not be vapor at that pressure, at that temperature, sorry. Okay. So below this pressure, this is ideal gas region. So we can treat it as an ideal gas. So water vapor is an ideal gas. The enthalpy of water vapor is only a function of temperature. In this gaseous region, in ideal gas region, enthalpy is only a function of temperature, not pressure. Only. So here you can see, for example, these are the enthalpy lines. So as we are in this region, whatever is the pressure, enthalpy is only a function of temperature. There is a constant enthalpy at that temperature. But here, this is non-ideal gas region. Here, your enthalpy is a function of not only temperature, but also pressure here in the non-ideal gas region. So for ideal gas region, enthalpy is only a function of temperature. That is also a concept from Thermo 1, somewhere you studied about this thing. That enthalpy is only a function of temperature for ideal gases or ideal gases. So enthalpy of water means enthalpy at any of this point. This is constant, so you can take it as Hg, whether water here, 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 wherever it is. Enthalpy is only a function of temperature, not pressure. So that's why enthalpy of water vapor at low pressures can be assumed as Hg at that temperature, in other words, because it's only a function of temperature. So these are just basic definition. Based on this, we'll discuss some more interesting definitions which are used in air conditioning. So enthalpy of water at 0 degrees Celsius is this much. Water vapor, Hg, at 0 is this much. So, and what is the temperature range? This one. So again, in this temperature range, we can assume constant Cp for water also, just like air. Okay, and that is this one. 1.82 kilojoules per kilogram per degree Celsius, that is Cp of water vapor. Okay, so we can find out enthalpy at any temperature. This is enthalpy at 0 plus Cp into T at any other temperature. Instead of using those steam tables, we can use simply that equation to calculate enthalpy of water vapor in this gaseous region. Yeah, Celsius. Temperature, in this case, it is specifically mentioned, that is in Celsius. Okay, so that is in Celsius. That is for the other units, BTU per pound, kilojoules per kilogram. That is enthalpy. Because here you can see, if you are using that equation versus the actual values from table A4, the difference is negligible. Enthalpy of water vapor from table means measured versus enthalpy of water vapor from this equation. For which region? Range? This one, minus 10 to 50 in vaporized region. So this difference is negligible, less than 1%. So that's why we can use simply that table instead of going to the table again and again. Simply use that equation to calculate enthalpy of water vapor. Okay. So now, based on these basic concepts, now we shall define some important definitions which are used in air conditioning applications. We'll start with absolute or specific humidity. So the next topic, absolute or specific humidity. Okay. So here, for example, we have air, and in this air, these are water vapors. So if I say mass of water vapor divided by mass of air, it is called specific humidity. Phi, mass of water vapor present in a unit mass of dry air. So mass of water vapor divided by mass of dry air. Total masses of atmospheric air is this one. Okay, so this ratio is called specific humidity. Whatever is the mass of water vapor divided by mass of air. There are two types of relative humidity. One is absolute, other is absolute or specific or humidity ratio. These are the three same terms. The other one is relative humidity. So this is specific or absolute humidity. Just this ratio is called specific humidity. Okay. Mass of vapor divided by mass of air. Now both are ideal gases. So that's why we can write in this form. For vapor, PV, partial pressure of water vapor, total volume is same. Okay. over R of vapor, because it is not in moles. If it is moles, then you write RU, but it is in terms of mass, so that's why R of vapor, R of air. Okay, same volume, same temperature, pressures are different, and these R values are different. Okay, so we can, so this volume will cancel with volume, temperature will cancel with temperature, so we can write it in this form. Now put the values of R, so here we have a constant. Okay, so specific humidity of air can be calculated using this equation if we know the total pressure and vapor pressure in it. So it's not, so we need to calculate vapor pressure by some other means, which we will see now. But that is the definition of specific or relative humidity, where PA is only the pressure of dry air. So it means you can write this term as P minus PV. Okay, total pressure minus vapor pressure. So here is the equation to calculate absolute or specific humidity or humidity ratio. Okay. Here P is the total pressure. Saturated air, when this air has maximum possible vapor in it at that temperature and pressure is most of the time we are on the earth, so it is 1 atmospheric. So when this air is saturated, means it cannot hold more moisture in it. So if you try to add more moisture, it will condense. So that is called saturated air. For example, air at 25 degrees Celsius and 100 kilopascal. So saturation pressure of water at 25 degrees Celsius is this much. Saturation pressure of water at 20. So it means this air can hold maximum this amount of water corresponding to this pressure. So PV, this vapor pressure will be 0 if it is pure dry air. If this vapor pressure is less than this value, then air is unsaturated. If PV is equal to this at this temperature, that is saturated. So saturated and unsaturated is clear.
Given that is condensation.
Yes, if you want to add more water vapor in it, it will condense. Or if you drop the temperature at this point, it will again start to drop. But at a particular temperature, pressure is throughout 100 kilopascal. At that temperature, this air can hold this much, maximum this much amount of water vapor in it. If the vapor pressure in that air is this one, then it is called saturated air, fully saturated air, or very humid air. And if the pressure is less than at that, if temperature changes, this value can change, right? High temperature, high partial pressure of water vapor, maximum, so it can absorb more water vapor in it. Okay, that's why in summer this air conditioner is not only cooling, it's also dehumidifying, because it is now air is at high temperature nowadays, so it has the capacity to hold more water vapor in it, right? So that's why water vapor is leaving, because now this temperature inside this air conditioner coil is lower than the dew point. We'll see dew point, but we already discussed something. Already it is lower than dew point temperature. So whatever air is coming in contact with this cold pipe, water is condensing because temperature is very low. At that low temperature, air cannot hold moisture. That's why water is separated and you see it is collected separately. So the maximum quantity of water vapor which air can hold depends upon its temperature, because this temperature will define the maximum vapor pressure. Okay. So what is this? Saturated air, amount of water vapor in saturated air at a specified can be determined from this one, at that pressure and at that vapor pressure. And maximum means how much maximum humidity means maximum vapor. So if I replace this PV with PG, I can find out maximum humidity ratio. This is vapor pressure at that temperature. At that temperature, if I replace with PSAT, so then I will get the maximum humidity ratio at that temperature. Okay, if you replace this PV with Psat, which is represented as Pg here, then the maximum possible. What? Yes, both PVs. Yes, both here and here, or only here. Okay. Next term is relative humidity. Specific humidity is actual mass over dry air. Relative humidity means that actual mass of vapor divided by maximum possible, again the mass of vapor in that air. So actual divided by maximum possible. If actual is equal to maximum, so you have 100% relative humidity. So it's vapor over vapor, mass of vapor divided by mass of vapor, actual divided by maximum possible. That is called relative humidity. Yes, that's what we will do now. We can write the specific humidity in terms of relative humidity. But relative humidity, basic definition is clear. Okay. So this will be a ratio, so it will be between 0 and 1 multiplied by 100. Okay. So that's how we define relative humidity, mV over mg, corresponding to such saturation point. Okay. Here we can again, we are treating both water vapor and air as ideal gas. So I can write this equation, this mass in terms of PV over RT. But now it's not air, both are vapor. Vapor, vapor, here it's also vapor. Here actual pressure, that is saturation pressure. Okay. So here volume, temperature will cancel, RV will also cancel, so only we will have PV over PG. Vapor pressure divided by maximum possible. Okay. So this equation 2 and this equation 3 in the from the previous slide, if you solve them where Pg is clear, Pg is equal to Psat, we can from here, for example, put the value of PV from here and put it here. So 2-3 steps, you can have an equation, relative humidity in terms of specific humidity. So we can find out relative humidity from that equation if the total pressure and saturation pressure at that temperature is given and specific humidity is known. So that relation can also be used. So now we have two equations, one for relative humidity, second for specific humidity. Both are derived from basic definitions, okay, and using ideal gas equations. Okay. So these are the equations. So 0 for dry air, 1 for saturated air. So the amount of moisture which air can hold depends upon temperature. So relative humidity keeps on changing if temperature is changing. So for example, specific humidity is fixed in an air. But if you change the temperature of this air, specific humidity will remain same, but relative humidity will change, right? So if specific humidity is constant, it doesn't mean relative humidity will remain constant. It may change with temperature. Okay. Next, enthalpy. Because in air conditioning calculations, we would be using these terms. Enthalpy is, of course, very important term. Now, enthalpy of air plus there is water vapor in it. Okay. So the total enthalpy will be enthalpy of pure dry air plus enthalpy of water vapor in it. So the enthalpy of atmospheric air consists of two parts. One is dry air, second is water vapor. So this is capital, so we can write it in terms of MAHA. mv hv. If we divide throughout with ma, because normally we express the enthalpy of atmospheric air per unit mass of dry air, right? Because that is the enthalpy of total air. But if you divide it with dry air, so that is the enthalpy which we normally use in calculations, enthalpy of atmospheric air per unit mass of dry air. So then, now what is the advantage? So here we will have, and what is this thing? Specific humidity. So we can express the enthalpy of air per unit mass of dry air as enthalpy of pure dry air plus omega into HV, enthalpy of water vapor. Okay. And if you remember in the previous lecture, we said that enthalpy of water vapor is only a function of temperature in this range, minus 50 to, 50 to minus 10. So this enthalpy of water vapor can be written as enthalpy of saturated water vapor. Okay. TS, for example. And these were the enthalpy lines, if you remember, below 50. These enthalpies are only a function of temperature for vapor. So enthalpy at this point can be assumed to be equal to enthalpy at this point for water vapor. Because this is easy to find out. So HV can be replaced with HG, enthalpy of water vapor, which is equal to enthalpy of saturated water.
H is the enthalpy of water vapor.
Yeah.
And Hg is the Hg in the table.
Yeah. HG you can easily calculate from the table. Yes. Yeah. Okay. So HV is nearly equal to Hg because enthalpy is not a function below this temperature, not above this temperature. Enthalpy is a function of temperature and pressure both. But below this temperature in which we are for air conditioning applications, this is a good assumption. Okay. So now we have the equation for enthalpy of air. Enthalpy of atmospheric air is equal to enthalpy of dry air plus specific humidity into enthalpy of water vapor. Okay, so that is the enthalpy. Now let's solve some simple questions. Here we have, for like this room, if you measure the temperature, it's 25, pressure is 100 kilopascal, relative humidity, how we can measure it, we'll see. But for example, here it is given 75% is the relative humidity. So we need to find out the partial pressure of dry air. Partial pressure of dry air means PA, we want to find out, which will be equal to P minus P of V. So total pressure is given 100 kilopascal. PV not given, so yes, temperature is given. So at that temperature, find out PG at how much? 25 degrees Celsius. That is for saturated, but multiplied by 0.75. This is what we did in chemical reaction chapter. So that will be vapor pressure corresponding to this relative humidity at 25 degrees Celsius. If relative humidity has 100%, so it is simply PG. Okay, so that will be at dry air pressure, pure dry air. Okay. Second part, specific humidity. So we just saw one equation, some constant into PV over PG, I think. Yeah, 0.62 PV over PG, PV over PG. This is specific enthalpy.
PV is Pj of Vj. So we have constant times specific.
Humidity.
Yeah,
No, not specific humidity. Relative humidity. Relative humidity. I don't remember the equation. Let me check. This is part A. Part B. 0.6. Yeah, it is PV over P minus PV. Yeah, this one. Not PG. PV over P minus PV. Okay. So the equation which we already saw or derived. So just put values. This is vapor pressure, actual vapor pressure, which is 0.75 of this thing. Okay. So that is the equation. Already shared the formula sheet. I think that is also there in the formula sheet. Okay. So you just need to know what is this formula. What is omega, what is PV. This is something you should know. The formula is there. Okay. So what is specific humidity? This much kilograms of water per kilogram of dry air. Okay, that is specific humidity. Now enthalpy HA plus omega into Hg or Hv. So HA plus omega, the equation which we just saw. Enthalpy per unit mass of dry air. So HA, enthalpy of pure dry air, Cp at that temperature. Omega and Hv can be written as Hg. We just discussed Hv is equal to Hg. So Cp of air, averaged Cp of air, 1.0. And Hg, either you have table. If you do not have table, we can also use this equation, which we discussed last time. This plus Cp dt. Hg plus Cp into temperature with respect to 0, minus 0 degrees Celsius, 0 is there. So then that is Hg. Or from, if chart is available, steam table is available, so you simply see Hg at 25. So this is air part, this is vapor part. How much vapor? It's not 1 kilogram, it is omega. There is omega 0.0152 kilogram. So just put values, Cp, average Cp temperature, okay, 63.8 kilojoules per kilogram of dry air. That is enthalpy of that air. Energy in that air, in other words. The total heat content in that air is this much. Okay. All these will be used when you will be designing a complete air conditioning system. Okay. Next, mass of the dry air and mass of the water vapor from ideal gas equation. Mass of dry air, pressure of dry air, not total pressure, pressure of dry air, volume of the room, Ra, and temperature, everything is given. So just put values where Va is equal to V of the room. Volume of air is equal to volume of vapor. Both are same. Okay. Volume of air is same as volume of vapor. Both are present in the same volume. Okay, so just put value. So that is mass of air in this room, for example. It is 85 kilograms of air present in this room.
The water occupies the same place as the air.
Yeah. Oh, if you think no, water vapor is concentrated in that corner. So, no, it's not like this. If you collect air sample from here, it will have same water vapor in it. Homogeneous mixture. Okay. Mass of air is this much. Now, how much mass of water vapor in that air? So the same equation, or we can also calculate this from omega. We already know omega is equal to mass of vapor over mass of air. So mass of air is calculated. Omega you already, so you can find out. Or using this equation, the same ideal gas equation for vapor. So pressure of water vapor, actual pressure multiplied by same volume, R of V. So water vapor R should be given. Okay. air you already know, but for water vapor it is 0.461. This was 0.28 for air. So that comes out to be 1.3. Although it is 75% humid, but still the amount of water vapor is only 1.3 compared to 85 kilogram of air. Okay. Or using this, you will get the same answer, 1.3 kilograms. Okay. Let's do another problem. Here we have a compressor. In this compressor, humid air is entering at 100 kilopascal. P1, temperature T1, and relative humidity is given at the inlet of that compressor. It is compressed in a steady flow isentropic compressor to 800 kilopascal, that is P2. What is the relative humidity of the air at the compressor outlet? Inlet is given, now condition is changed. Pressure is increased, so temperature will also. Isentropic, so it means all maximum temperature increase will be here. So this dome is for water, not for air. Okay. So for example, this is 0.1 with respect to vapor, water vapor. TS. Now it's all about TS. Okay. From this subject onwards, it's all TS. TS in power plant, it will be only TS. In refrigeration, it will be pH. So pH and TS. PV, if you are solving turbo machinery subject, these compressors, if you study again, then PV. Okay. So 1, 2, 2. So pressure increased, temperature is increased. So what you expect? So here the relative humidity is how much? 20%. So what you expect here, relative humidity will 90, sorry. Much less. Because temperature is much higher, now there is a huge difference from the dome. So it will be less. So how less? That's what we want to find out. So at point 2, we want to find out relative humidity, and we know relative humidity is given by PV2 over PV2, that pressure. Yeah, at that temperature. Sorry, that is temperature. This is P2. I have drawn so much high because I need to show this thing. Okay, look, P2 over PV2. This is relative humidity. Okay, hopefully compressor has not compressed so much that you are above the critical point. Okay, so this P2 divided by PV2 is relative humidity. So we need to find out these two terms, PV2 over PG2. Okay, so how to first find PG2? How we can find out PG2? If I know the temperature. So I need to know this temperature so that for that temperature I can find saturation pressure. So that will be PG2. Okay. At this will be PG at T2, which is not known. How we can find out T2? Yeah. T2 by T1 is equal to P2 by P1 to the power K minus 1 over K. For air, whatever is the temperature of air, that is same for water vapor. So P2 and P1 are known. Let's find out T2, and from there PG2. So PG2 is now known. Now we need to find out PV2. For PV2, isentropic is used now to calculate T2. Now how to calculate PV2? PV2, there is one equation which we studied. For PV2, if I know specific humidity, because PV2 is present in this equation of specific humidity, which we derived. So we'll try to find out PV2 from here if I somehow can calculate omega 2, specific humidity. This was the formula of specific humidity at any point. So if I know specific humidity, that is the one equation which I know, which can give me PV2 at point 2. So specific humidity from 1 to 2, did it change specific humidity? No. Specific humidity did not change from 1 to 2. So it means if I can calculate using this omega 1, this will be equal to omega 2, which can give us PV2. What is given? Final pressure of the whole air. We want to find out the final pressure of the water vapor in that air. Okay. So to solve this, so you can write this equation in terms of PV2, which we want to find out. So just simple mathematical steps. So we have written PV2. So I need omega 2, and P2 is already known, total pressure. So omega 2 is equal to omega 1. Same equation at point 1. Now at point 1, P1 is given, PV1 is also given. 0.9 of P set is PV1. So just put values, PV1, okay. Now it's clear, just follow the solution. So you will have PV2 finally. So PV2 is now known, PG2 we already discussed, okay. Omega 2, this is to calculate temperature, so corresponding to this temperature, Pg2 at P set at 258, this is 258. Temperature has increased to 258, and 258 is less than critical point. Critical point is 374 for water, so we are below this one. Okay. So Pg2 is P set. So now everything is known, just put values. PV2 is calculated, Pg2 is calculated. So relative humidity is dropped from 90 to 30, not 37, 0.37.
You can't use constant enthalpy.
Constant?
Enthalpy.
Where I used constant?
No, we didn't use it. We didn't use it.
Yeah, enthalpy, there is no question of enthalpy here. You just need to calculate relative humidity at 0.2. So now you can see relative humidity has dropped to 0.37% from 90% to, if you increase its temperature from 20 to 258 degrees Celsius, same air, its relative humidity is dropped so much. Okay.
So there are many equations. How we can know from where we have to start the problem?
Yeah, practice. Practice. All equations will be given.
So I will write all the equations.
Now, if you are doing this thing right in the paper, if you didn't practice before, yes, then you have to do it like this. So practice it before. That's what. Okay. Next, let's move on. The next is dew point temperature. So all these terms actually we studied in combustion. So here in this figure, for example, this is point 1 is the vapor pressure in that given air. Okay. So if you start cooling this air, for example, this air comes in contact with soda water. Air temperature is low, so this air temperature will drop. So it will follow the same line, same pressure. And if it reaches here, it will start to condense. And normally, so soda water temperature is normally lower than the dew point temperature of that air.
The soda Victoria is in where? In the atmosphere.
That's an example. For example, this is 5 degrees Celsius. Here you have air at 20 degrees Celsius.
It's outside.
You just bought a soda from the canteen, okay? Now you came outside, and after some time, what you will observe there on the outer surface. So that's what I'm trying to say. So you just bought that soda water, which is very cold. So now this air comes in contact with this soda water. For example, soda water temperature is here, 5 degrees Celsius. This was the initial temperature, 20 degrees Celsius. Now when this air comes in contact with this surface, so the temperature of the air starts to drop. Sorry, water vapor. Water vapor present in that air. Yeah, so this water vapor temperature is starting to drop. At this point, because the temperature is still lower than this, but at this point, this water vapor will start to condense.
It's not in the air. Around the
Yeah, that portion of air which is coming in contact with this soda water. Okay, or okay, leave this example. This air in this room, when it comes in contact with this one, water separates. Why? This air gets cooled up. So water vapor present in that air is also getting cooled down. So that's why when it reaches here. So during this process, is specific humidity changes during this from 1 to 2? No. At point 2, no specific humidity will drop.
Yes.
Right? So it's this process is constant specific humidity process, but relative humidity starts to drop, change. Here it has low relative humidity. Now it's 100% here at this point. So this point, this temperature at which water starts to separate from air in the form of liquid is called dew point temperature. Temperature at which condensation begins when the air is cooled at constant pressure. So this is actually the saturation temperature of water. What this temperature is, saturation temperature of water corresponding to this vapor pressure, in other words.
Humidity is 100%.
Yes, at that point. Okay. So TDP is actually Tsat at that pressure. So water vapor in air exists in superheated unsaturated air. Now it becomes saturated. Okay. So during this cooling process, vapor pressure remains constant. At this point, it starts to, now vapor pressure will start to drop in that air because water is separating. Okay. Go through. We discussed all points. Okay. Now at this point, what happens? Water starts to separate. What about the air? Air temperature, because air will continue to condense. Air temperature will continue to drop till 5.
No.
Now water rise up or go down. Temperature is dropping. So air. So after this, it will be a look, the last line. Air remains saturated. Whatever air which comes in contact with, which is at this point, it is in contact with this one.
Yes.
So from here to here, it will follow. This condensation process will continue and follow a path of 100% relative humidity. So now air temperature is dropping and it is following this path of 100% relative humidity. Look.
This is what is the graph, right?
So air temperature is dropping, right? It will continue to drop, and but during that drop, Relative humidity is now 100%. Air is coming in contact, and water is getting separated, because this temperature is lower than dew point temperature. Okay. Let's see here, for example. In winters, what you observe, inside air is, for example, 20 degrees Celsius, and it is 75% humid, relative humidity. Now it's again cold. Outside is cold at 10 degrees Celsius. So what you can observe during winter, if you touch this glass, winter, it will be cold, colder than room air, right? So inside, you will have such temperature profile. Inside, in the middle of that room, high temperature, and it is dropping towards the window or wall, because outside is 10, for example. Okay. Now, what is the question? In cold weather, condensation frequently occurs on the inner surfaces of the windows. We observe this thing in car windows actually, due to the lower air temperatures near the window surface. Wherever the temperature is low. Look, here this is outer. Maybe it's a corridor, okay? That is also cold. Inside you have air conditioning, some heater, but outside is cold, whether it's corridor or some outside, okay? So inside air is at 75% relative humidity. At what window temperature will the moisture in the air start to condense? Here it is given that window temperature is 16. So will the water present in that air start to condense here or not? That is the question.
So we calculate that. Now what is our 16 or 10?
Currently it's 20 air. Now it is dropping here. So for this air at 20 degrees Celsius, again Ts, corresponding to 20 degrees Celsius, there is this saturation pressure, P set at 20. So what will be pressure here, actual pressure of air?
75 times.
Yeah, so here it will be somewhere here, 0.75 multiplied by P set at 20. This is your air temperature. Sorry, air pressure. Temperature is 20. Now this air, when this air will cool down, vapor pressure, in that air, vapor, okay, vapor pressure, okay. So this is that PV. Now it is getting cooled when it comes in contact with some cold surface, colder than this. Means it, when it will come in contact with the surface which is colder than this, so its temperature will start to drop at the same pressure, and it will condense at this point. So now what is this point? T set at that pressure. Okay. See again, this is room air at 20 degrees Celsius temperature, and how much pressure? It's not 100% humid. It means this point is not this one. If it is 100% humid, then this will be the point. It is 0.75 of 100%. So multiplied by 0.75, you will be somewhere here. Lower pressure. Now at this pressure, what is the dew point, in other words? T set. So at that pressure, if you cool it, this will be the T set. T set at that pressure. So now we need to check from the table what is T set corresponding to this pressure. If this T set is 16 or higher than 16, there will be condensation. Or lower, your air has not reached that temperature. Here, according to this figure,
16 or higher.
minimum is 16 here. So we need to check whether this is also 16 or higher.
So it will not.
It will not condense.
And then
Below this, it will condense. So this temperature, for example, I think it is something 15 point something. This T set. Now here it will condense? No, because still temperature is here 16 something, near. So I explained this thing with the help of this diagram. Okay, so this is PV and dew point temperature at that PV is T set, which is 15.4. Okay. Let's move on. Now it's some more terms, adiabatic saturation and wet pulp temperature. Look, in these questions which we have solved so far, one thing was always given, relative humidity. So for example, in this room air, I want to measure relative humidity. So how to measure it? That's why we have next. So because in air conditioning applications, we are very much concerned with the amount of humidity in that air. That defines our thermal comfort. So for any air present in our surrounding, if I want to find out how much is the relative and specific humidity, how can I find out? Here it was given so far, and we know those equations, but in those equations, some unknown things. So one of the way is to use this concept of relative humidity. Look, this is air, for example, this room air at that temperature. Okay, so I know only the temperature of that room air, and I also know the total pressure, which is 100 kilopascal. Okay, I do not know PV. How can I find PV? With the help of that concept of dew point temperature. So what I will do, I will make this air to cool down. No, I will not calculate this. I am cooling this air, I am noting its temperature as it is dropping, but the temperature at which condensation will start, I will note down that temperature. Yeah. So what you are doing, you didn't know what is PV, this was unknown. So you started cooling down this air. At that temperature, dew starts to come out, or water vapor starts to condense. So I know the temperature now. So it means corresponding to this temperature, what is P set? So it means your air was at that pressure because it is a constant pressure. So now I know the pressure. I have calculated the pressure using dew point. I measured the dew point temperature corresponding to this. This is P set. So now I know PV. I want to find out relative humidity. What is relative humidity? PV over PG. Now I know PV. And I also know T1. Yeah, so corresponding to this one, at that temperature, this is P set. So PV over P set, I can find out relative humidity. So look again, temperature, only temperature was known. I cooled that air, and the temperature at which dew starts to come out, I noted down that temperature. So at that temperature, this pressure is PV. This was the initial pressure. And at that PV, find out what is, actually temperature was already given. So now we know T1. So at that T1, what is P set? So PV over Psat at that temperature corresponding to this temperature, this is Psat. Right. So if your concept of chapter 3 of Thermo 1 is clear, then these things are not difficult. Okay.
You are doing all this because you don't know PV.
Yes,
But
yes.
in the reality, we know the total volume of the
No, 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 no. We know only the total pressure.
total pressure.
Total pressure.
Total volume.
Okay, total volume. I do not know the volume of that air outside. Okay, so what is outside air? So, okay, calculate volume if you can. So, right.
Total pressure. Initial volume.
Initial temperature you can measure easily. Okay, and final temperature after cooling that air. So now you know that temperature. So corresponding to this temperature, whatever is Psat is partial pressure of water vapor in that air.
The final temperature of a
Psat of the yes. Actually, this is not Psat. You are making it to make Psat. Yeah, that's this Psat corresponding to this temperature.
The final temperature over the initial
Okay. Clear? So this is one way to calculate relative humidity. So once you know relative humidity, we have another formula of specific humidity in terms of relative humidity already. So once you know relative humidity, we can find out specific humidity also. This is one way, but there is another way, which is called adiabatic saturation temperature. This is another technique to find out the specific or relative humidity in a given air, whatever is air is present. So I explained only this one sentence, okay? By knowing the dew point temperature and relative humidity can be determined, which I explained here. Okay, that is not explained in the book. He is expecting that you should know it. Okay, now this is the second method. What is that second method? That is called adiabatic saturation temperature. Now look here, what is happening here? Air is entering. This is the air for which I only know temperature and pressure. I want to find out its relative humidity and omega. Relative humidity, how we are representing it? Phi? Yes, phi. 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 This is psi. Exergy. Okay. This is phi, also exergy. This is phi 1. Okay. Do not forget those things. So that's what I want to find out. This is given. So what I do, I make this air with known pressure and temperature to flow over a liquid. Liquid is present in that tank, and this tank is heavily insulated, so means no heat transfer, the adiabatic world. Okay. Now this air, it is made to flow over that water. So some of the water vapor will, some of this liquid water will evaporate when air is made to flow over that water. And this tank is long enough that you are making sure when air is coming out of it, it is completely saturated. So unsaturated air entering, and we are getting saturated air, means phi 2 is 100%. And we can measure the temperature T2, and here whatever air evaporates, we supply more air so that this level of liquid remains constant. So it means I know at what temperature I am sending this water. You know the difference between boiling and evaporation? Boiling only occurs at boiling points. Evaporation is occurring at all temperatures from the surface. Some of the molecules are all the time evaporating. Depending upon air, if air is very less humid, so more water vapor can accommodate. No evaporation. Sorry, yes, there will be no more evaporation. Okay, if you made it so long here till here, for example, and here 100% humidity is reached, so after that nothing is happening. It's the same air is going out.
How to know what is the long? Because final error.
There are so many other ways. At what speed air is entering, what is the length of that, what is the temperature, what is the width of that channel, and so many other things. So look what is given and what we are calculating. Temperature and pressure we can easily measure. Relative humidity and specific humidity we want to measure using these values, temperature and pressure. So here T1 was known, pressure is atmospheric pressure. Here temperature, what will happen to here when the air will be coming out of this tank? Temperature will drop or increase. Okay. So if the temperature of the liquid is smaller than air, look, when air is evaporating when this liquid water is evaporating in that air, for evaporation it needs heat. So from where this heat is coming from? From the air itself. When air evaporates, when water evaporates in that air, to evaporate that water, it needs some energy. And the only energy source here is air. So during this evaporation, temperature of water will not change. It will be at T2. Must be lower than T1, yes. Yeah. So here the temperature of the air will drop when it comes out here. And when it is relative, and minimum temperature which you can achieve here is the same as this one, T2. That is called evaporative cooling. Evaporate just by evaporating water in unsaturated air. Air should be unsaturated. So it will absorb water vapor, but the heat of evaporation comes from the air, so temperature of air drops. Temperature of water is not increasing because it is evaporating. Okay, so now T1 was known, now T2 you calculated here, and because it is 100%, so now you know the relative humidity here, T2 here. Now we will apply mass and energy balance to find out this omega 1 or phi 1.
The air, the temperature of air is greater than the temperature
is greater? Yes, greater. Yes.
Because of that, there will be a transfer. So I have T1 and T2. I will use
Heat transfer and mass transfer because water is evaporating in that air. So that is heat and mass transfer. Yes.
I know the T1 and T2, so I use the same methodology that I use in this sentence.
Which methodology?
I know T1.
Okay, that will be clear as we will see. Okay, this process from 1 to 2. During this process, what is happening to the pressure?
Does not change. Does not change.
No change. Why? Water is entering in that air. Here from P1 to P2, pressure of air. This was kind of dry air with less water vapor. Now water vapor is added in it, so pressure P2 will be greater than P1, but temperature T2 will be less than T1. So let's see here. This was state point 1. So from 1 to 2, pressure is increased, but temperature is T1, T2. But pressure is increased. Total pressure of that air because water vapor is evaporated in it. Yeah, because of this mass, pressure of this air has increased. Pressure of air. In that pressure, what is adding? Partial pressure of water. More water vapor is adding in it. So the total pressure has increased here. So that is a general diagram showing that during this process, what was happening? Temperature was dropping, pressure was increasing. We do not know the exact path, that's why we only know the end state, so we have joined with dotted lines. Okay. Now we shall use this thing to derive an equation for omega 1. Difficult to digest? So let's move on. So whatever we have discussed, it's written here. Let's go through, and we are making sure that your relative humidity becomes 100% and temperature T2, which is known as adiabatic saturation temperature. Because during this process, no heat is going into the ambient, that's why adiabatic, and temperature here is saturation temperature. Look, 0.2 temperature is saturation temperature. Corresponding to this new PV2. PV2 is higher. Yes, now we will develop an equation. What we can calculate? No, here, what we know, relative humidity, temperature we can measure, and here inlet temperature was known. Yeah, T2 is equal to Tsat, or the temperature we can easily measure with the help of a thermometer. Okay. So now first apply mass balance to this one. Now we are trying to derive an equation of unknown omega 1. So mass balance means mass of air entering must be equal to mass of air leaving. So mass of air will remain constant from here to here, pure dry air, dry part of that air, dry air. So mass of dry air at point 1 is equal to mass of dry air at point 2. So simply write mass of dry air. What about mass of water vapor? Yes, mass of water vapor, this at mv1 plus m, it is named as m of f liquid, which is boiled and you supplied here. Okay, so mw or mv1 plus mf must be equal to mv2. Mass of water at point 1 plus, which is supplied, must be equal to mass of water at point 2. So from here, so that is the water. Now if I use this definition here, we know mw over ma is equal to omega. So I can write this mw1 as omega into ma1, omega 1 into ma, mf is pure liquid, and here m dot a into omega 2, m dot a into omega at point 2. So I can write the same thing in terms of mass of air. So from here I can write the equation of mf, which we supplied, in terms of omega 1 and omega 2. Although those are unknown, but we'll develop an equation. That is from mass balance. Okay. Mass of dry air, mass of water vapor, and we wrote this equation in terms of mass of air. Here, mass of water is replaced with mass of air multiplied by specific humidity from this definition. Okay, similarly at point 2. Okay, so from here I wrote an equation of m dot f. Now this is mass balance. Now let's apply energy balance. So what will be energy balance? Energy entering must be equal to energy leaving. So what is energy entering? H1. Yes, E dot in must be equal to E dot out. There is no heat transfer, no work done. So mass of air entering into H1 plus look, we write enthalpy in terms of per unit of dry air. So multiplied by dry air. No, this is the enthalpy of both water and air. H1, the equation which we derived for H1, we will now put here, and that is for both air and water
Yes, but
per unit mass of dry air. H1 was equal to H of air plus omega into H of vapor,
over mass.
mass of air, multiply the mass of air per unit mass of air. That's how we defined enthalpy. Okay. So m dot A H1 plus m dot F HF at point 2 is equal to m dot A H2. So here now m dot F we can replace with, so now we have throughout m dot A in that equation, mass flow rate of air. Now m dot F is replaced with this in terms of m dot A. Now MA will cancel throughout. Okay. So dividing by m dot A, so that is the equation H1. Now what is H1? Enthalpy of dry air plus omega into HV, which is Hg we can write. This was enthalpy of air plus omega 2 minus omega 1 HF2 is equal to, that is omega enthalpy of air at point 2. That is enthalpy of pure liquid water which is entering here. Omega H of V, which is equal to H of G. So now from here I can write an equation of omega 1. Unknown specific humidity. Omega 2 we can find out. It is 100% saturated. So from here I can find out omega 2. You are making sure that it is 100%. Nowadays we have very good instruments which directly give us the, so behind those instruments such calculation is being done. So T1, T2 temperatures which we can easily measure, CP of air, omega 2 at 0.2 which is 100% saturated, I can find out omega 2, and HFG2 at that for that water. Okay. So here is the omega 2 which you were talking about. We know the omega 2 general equation, but I know the pressure now. This is its saturation pressure. Okay, Pg2. Saturation pressure corresponding to whatever is that temperature. Okay. Okay. So using those equations, we can find out specific humidity or relative humidity using that equipment which is called adiabatic saturation temperature. Now, two more concepts. Okay. Same thing which we are doing here, that dry air is made saturated. Same thing we can do using another way, simpler way. So here we'll define two new terms, dry bulb temperature and wet bulb temperature. If you measure the temperature of this air using any thermometer, that is called dry bulb temperature. But if you cover that bulb of that thermometer with a wet cloth, some wet cloth, and then you make this thermometer to move, so what will happen? Water will evaporate. So here you will measure the wet bulb temperature. Temperature will drop because water is evaporating. So for the same air, we can find out the wet bulb temperature. Now,
I'm making the air around the bulb 100%.
Then there will be no temperature drop. Then dry bulb and wet bulb temperature will be same.
Yeah, I mean the temperature around the bulb I mean the air around the bulb 100%
Saturated, yes, yes, that's what you are doing. Exactly. So wet bulb temperature means when you measure the temperature of air by covering this bulb with some wet wick or cloth. So it will give you lesser temperature because some of water will evaporate how much depending upon the air temperature. What is the maximum it can hold? So that amount of water vapor will evaporate. So due to that evaporation, again, its temperature will drop because it's just like evaporation. When something evaporates, you feel cool because water takes heat from that body. Okay. So if unsaturated air passes over it, the temperature drop will be more compared to saturated. So it means you are calculating this temperature, in other words. Okay. If the surrounding air is very dry, this T wet bulb will be much lower than T dry bulb. If the surrounding air is already 100% saturated, then TWB and T wet bulb will be same. So in other words, T dry bulb will always be greater than or equal to. So T wet bulb can never be greater than T dry bulb, in other words. Okay. Now, the same we can measure using this mechanism which is called Sling psychrometer. Here you have two thermometers. One is uncovered, normal. Other is covered with wet cloth. Now you swing it until the temperature of this is not changing anymore. So note down these two temperatures. One without cloth will be dry bulb temperature. Other one with wet cloth will give you wet bulb temperature. This is called Sling psychrometer. So now we performed that experiment and we measured these two temperatures. One is dry bulb, other is wet bulb. Now using these two, we can find out all these specific humidity, relative humidity, etc. Look, so you do the dry and wet bulb temperature of atmospheric air are measured to be 25 TBdB and TWB. Okay. So I'm using the time of yesterday's tutorial. Okay. So TDB is equal to 25 TWB wet bulb temperature, and this is the equation which we just derived to find out specific humidity. So what are these? So you have to use that table to find out what is omega 2. Omega 2 we know, simple equation. So Psat at 15 degrees, at 0.2. Psat at 15 degrees Celsius. So which you will find from here. Find out omega 2. Okay. And next put the values. What is HFG2 at 0.2 at that temperature? 0.2, 15 degrees Celsius. HFG2. Okay. 2465.5. All right. T2, T1 clear. HG1 at 25. HF2 at 0.2. This is the equation which we derived. But we needed these two temperatures. So instead of using that adiabatic saturation, use that mechanism, Sling psychrometer, it is called. So we can find out specific humidity. Yeah, it's the same principle. Relative humidity, this is the equation which we derived earlier. Relative humidity in terms of specific. Now omega 1 is known, so P2, Pg2, just put the values. P2 is the total pressure, Pg2, Pg1, vapor pressure at 0.1. Okay. Omega 1 you already. Enthalpy of this air consists of two parts, dry air and vaporized part at 0.1. So CPT1 plus omega 1 Hg1. So just put values. So instead of using these equations, we have charts. So we can directly find out if any two parameters are given, we can find out all other parameters. And this chart is called psychrometric chart. So instead of using those equations, by solving those equations, those charts are developed, which is called psychrometric chart. So in that psychrometric chart, here you see dry bulb temperature on x-axis, here specific humidity. Okay, this is saturation line, means phi is equal to 100%, and here you will have phi is equal to 90 and so on up to 0. Phi means saturation, relative humidity. And here you see constant specific volume lines, constant enthalpy lines. These are enthalpy lines, and also you have wet bulb temperature lines. So, no, a little bit. There is a difference, but very small. The slope is different, but very near. The wet bulb and enthalpy are very kind of parallel. Okay. So these are some basic lines are shown. So these can be used to find out different properties. So here is the actual chart where you cannot read anything. But when you take a print, it is readable. Now let's solve a simple problem, and you will see that's much easier than using equation. Okay, so let's solve a numerical. And one interesting thing here you can notice, here you also have these temperatures are written. This is dry bulb temperature. This is specific humidity on y-axis. Now you have temperatures. For example, at this point, this is 100% relative humidity. At 100% relative humidity, dry bulb and wet bulb will be same.
Yes.
You just saw 100% relative humidity means this dry bulb and wet bulb both will have same value, 15 degrees Celsius. And also dew point, that is also a dew point. This is dry bulb, wet bulb, and dew point. Dew point temperatures are, for example, this is the condition of your air. It's not 100% relative humidity. So I can read its dry bulb from here. Okay. This will be dry bulb temperature. Now, if I want to find out what will be the wet bulb temperature, wet bulb means if you add moisture in it to 100%. So it means, so here are the wet bulb temperature lines. So there will be wet bulb temperature line going through here, and you can read the wet bulb temperature here. Look, from here to here, what is happening to humidity? Increasing. That's why you see wet bulb temperature lines are like this. Okay. What about
here temperature below from left to right is increasing?
Yes, here it's left to right is increasing.
And from down to up, temperature is increasing.
Yeah.
For dry.
No, dry bulb is here. For that air at point 1, dry bulb is this one. I want to find out for this air what will be wet bulb temperature. If the same air, if you humidify this air, so its temperature will start to drop and specific humidity will start to increase when you humidify that air. So it means you are reaching this point, 100% relative humidity. So this line which is passing through here, through this point, is its wet bulb temperature. Dew point, what is dew point? You do not add water vapor in it, you just cool it. So it means specific, constant specific humidity. If you follow from here, constant specific humidity line, this will be dew point, dP. It's too much.
It's way too much.
Yeah, it's too much. Okay, we'll be using it in refrigeration, air conditioning. Here, simple question. Let's solve that question. For example, here there is this room contains air at 1 atm and 35 degrees. So what is this temperature? Dry bulb. Normal temperature which you measured. And 40% relative humidity. So that is relative humidity. So these two are given. Now we need to find out all these either using equations or using that chart. So let's use the chart. This is something we will learn in air conditioning, okay, in detail. Here just to introduce that chart. So here is that chart. What is given? Dry bulb temperature and relative humidity. So you need to trace this point. So dry bulb temperature is 35. Can you read? Temperature is increasing in this direction. So that is dry bulb. So here is 35. You cannot read. 35. Yeah, you're right.
It's not the black one. It's the box.
Yeah, the
It's
upper
not
one.
clear.
Here it's 35. This is dry bulb temperature line. Okay. This is something else. This is enthalpy. Yes. These are enthalpies. Okay, let's see. You will find different versions of those psychrometric charts. Someone is showing enthalpy here, someone is showing enthalpy. Look here, also enthalpy shown. So all these lines are actually, they are meeting here. There's one enthalpy line. You can read enthalpy from here or from here or from here. Look, these are enthalpy lines. So dry bulb temperature is here, which is not clear here, but that will be clear on paper print. So you draw up, because dry bulb temperature lines are vertical. Next, 40%. So humidity lines are, these are these blue lines. These will be 100, then 90 and so on. These blue lines. See? So here is a blue line. This one, this is 40% and it is written somewhere. Here it is 40%. So now you have the intersection. Now we can find all others. So we need to find out specific humidity. This is specific humidity. So draw a horizontal line to read specific humidity here. Or so there is specific humidity, which is written here. Okay, its units are also written, kilograms per kilogram of dry air. So specific humidity is horizontal. This is wet bulb or enthalpy. Both are almost parallel. So you can read enthalpy or wet bulb, enthalpy. So these are the enthalpy lines. So read enthalpy 71.5 per kilogram of dry air. Enthalpy of air per kilogram of dry air. Okay. So now enthalpy is done, specific humidity is done. Next is dew pointing, wet bulb temperature. So same line, but wet bulb are written here. These are enthalpies, so wet bulb are written here. These blue, this is 20, this is 25, so you will say 21, 22, 23, 24 almost. Wet bulb. These are wet bulb temperature lines. Next, dew point, same horizontal. Here you read specific humidity, but here this will be dew point. So this is wet bulb, so this is dew point. Same scale, but now it is 15, 16, 17, 18, almost 19 point something. 19.4. So it's easier or using those equations. Okay. So this is a chart which can be used to find out air properties, and if the same air becomes 100% saturated by following this line or by following this line. By following this line means you are adding moisture in it. By following this line, it means moisture is fixed, you are cooling it. You are cooling it. It is this line, it is following this line. You are cooling the air.
And the other one is
When you are humidifying the air. That's when you are humidifying the air, evaporative cooling. Then you will be following this line. Okay. In both cases, temperature is dropping because this is a drop in temperature. Dry bulb increases in this direction. Okay. What else? One thing, specific volume. These black lines are specific volume lines of that air per kilogram of air. So here is one example. Also, another examples you can solve it. Here it's English units. Okay, English units, BTUs, and those are. Leave this thing. We'll do it in the air conditioning, refrigeration. Okay, let's leave it.